Ladies and gentlemen, welcome to AP Video 3.1. Here we are looking at atomic mass and the mass spectrometer. Main objectives are to describe the atomic mass scale and explain how atomic masses are experimentally determined. Just a reminder, make sure you turn off all of your cell phones. Make sure your social media is put away. I highly encourage you to pause and rewind as needed. And if you should need to, put some notes in the margins so you can ask those questions later. Alright, let's get going. So determining the mass of atoms. Well, the most accurate method that we have right now is a device called the mass spectrometer. It helps us find the mass of atoms and compounds. In this device, particles are separated by their size or mass, and their relative masses can be determined. Let's take a look at how this works. So in a mass spectrometer, which is the device on the right here, here's the schematic for it, your sample is inserted into the mass spectrometer, and the heating device vaporizes the sample into a gas. And then that gas is pumped through the machine. An electron beam basically will cause the sample to turn into positive ions. And now that they're positive ions, when they are put through an ion accelerating field, it causes those ions to rapidly shoot through this area here. Now that accelerated beam will pass through a magnetic field, and that magnetic field then, because it's positively charged now, it can actually cause it to deflect. And essentially, the different particles will deflect as they go through here, and they're detected over here on the detector plate. Now, why do we believe the least massive ions hook up this way, and why do the most massive ions get detected over here? Well, when they're least massive, the deflector has more impact on them, so it deflects them more and they shoot up more up to this area. And the more massive particles, they don't want to move their direction very much, so therefore they deflect least and end up over here. So the detector basically counts how many particles are hitting here and how many particles are hitting here and so forth, and the output of it looks something like this. So relative number of atoms, it's kind of like a percentage essentially. So relatively, out of 100 atoms, 91 of the atoms had a mass number of 20. About 0.3% of them had a mass number of 21. And about 9% of the atoms had a mass number of 22. So here we're talking about some element X that is the isotope of mass number 20, isotope with 21, and then an isotope with 22. And if you look at the periodic table, an element that's really close to those particular masses would be neon. Okay, so a mass spectrometer can basically identify an element by running a sample like so. And then from this, you'll see later in the video how we can calculate atomic mass. Carbon-12 is the standard, so the atomic mass unit, AMU, should be lowercase there. The modern system is based on carbon-12, which assigns carbon-12 a mass of exactly 12 atomic mass units, AMUs. All their masses are relative to this particular standard, so basically scientists came up with a standard element to determine this new unit for massing atoms. We don't want to use grams or kilograms, this is way too big. The AMU is used for massing atoms, and it's based off of carbon-12. So what is atomic mass? Well, when you look at the periodic table, oftentimes if you look at a symbol, like for example carbon, its atomic number is 6, and in the bottom left corner there's another number here, and that is the atomic mass unit. And it's usually a decimal number. So they're not whole numbers like mass number. Don't forget mass number is protons plus neutrons, and it's going to be a whole number. So for example, carbon-12 would be 6 protons plus 6 neutrons equals 12. Carbon-13 has 7 neutrons, and therefore its mass number is 13. This number right here is the atomic mass. And the atomic mass, or sometimes called average atomic mass, is what's reported here. The average atomic mass is not a regular average, it's a weighted average. So atomic mass is a weighted average of the atom's naturally occurring isotopes. And we have a way to calculate for that. So every element consists of naturally occurring isotopes of atoms. So again, like we have carbon-12, we have carbon-13, and we have carbon-14. They occur in different abundances. Carbon-12 is very abundant, carbon-13 is barely abundant, and carbon-14 there's just like a little bit of it. And that mixture there though, it's a constant mixture. So anywhere in the universe we get this constant mixture of a lot of carbon-12, a little bit of 13, barely of carbon-14. Now to calculate the atomic mass, what we're going to do is we're going to take the relative abundances. So it'd be like some kind of percentage. So something like, if it says like 98%, we're going to use it in decimal form. And then we're going to multiply that by the mass. So if it was carbon-12, it'd be 0.98 times 12, and we add them all together. So if that was for carbon-12, now we do it for carbon-13, and carbon-13 times its percentage in decimal form, plus the percentage of carbon-14 times its decimal form, and you add those together. So let's actually do a problem so you can see how this looks. So, look at that, it's basically the one we want to do. So, carbon is composed of 3 isotopes, carbon-12, 13, 14. To find the atomic mass, you're going to take the decimal form of the abundance, so 0.9889 times 12 plus 1% is 0.01111 times carbon-13, that's the mass there, there's the mass there, plus carbon-14 is negligible, so it's almost got 0% essentially, so we're not going to even really do that one. So this times this plus this times this equals 12.011 AMUs. And that is the average atomic mass for carbon. You can always verify this. It should be very close on the periodic table. Sometimes it might be a little bit off because of sig figs, but it should be pretty darn close. And that's how you find atomic mass. And although we've already finished the problem, I do want to just back up for one quick second there. These numbers I'm getting, the 98% and the 1% here, don't forget those numbers come from the mass spectrometer we started the lecture with. So it detects the information here on the mass spectrometer, and it gets you this output of data of these different percentages. That's where those numbers would come from in this particular problem. Alright, good job everybody.